Good afternoon, everyone. Well, thank you very much for connecting to this webinar about the Upscale project. I think we're going to wait maybe a couple more minutes so to let other people connect to this webinar. Thank you. Okay, well, I think we can start in order to avoid getting too much behind schedule. Well, good afternoon again, everyone, and thank you very much for attending this webinar organized by France Énergie Marine about the Upscale project, which focuses on the topic of characterizing ever higher offshore wind profiles for accurate prediction of turbine performances. My name is Jean Dubranat. I'm project manager in France Énergie Marine, and I'm very involved in the development of this Upscale project, along with my two colleagues, Nel Luxey and Marion Coquelet. Just a few words about the content and the objectives of this webinar, so you know where we are going. Very soon, I will leave the floor to Nel Luxey, who will present France Énergie Marine, our research institute. We will continue by presenting the context of the Upscale project. Then my colleague Marion Coquelet, with her, we have decided to present the technical content of our project to a short list of relevant entities, which is the reason why you have specifically been invited to this webinar. And well, I'm sure that even before the end of this presentation, you will want to become part of the consortium by joining us, of course, under certain conditions that will be presented to you in the last part. So, moving on to the presentation of France Énergie Marine, I will now leave the floor to Nel Luxey. There you go.
Thank you, Jean, and good afternoon, everyone. My name is Nel Luxey. I'm in charge of the Wind and Ocean Dynamics Department in France Énergie Marine. I will now say some few words to quickly introduce our institute. Our institute is focused on innovation in offshore wind, specifically, and marine renewable energies in general. And what we aim at is a strong industrial impact and strong economic and societal impact. We are about 90 employees. Most of them are researchers. We exist since 2012. To give you an order of magnitude of our activity in 2024, our activity was about 10 million euros. We are based in France. Our headquarters are in Brest, and we have also offices in Le Havre, Nantes, and Marseille. We also have an agreement with the French Research Agency that makes us an institute for the energy transition, and that allows us to be supported by the France 2030 investment plan. We are not working alone, of course. We are working with members of the Institute. Some of them are from the industry sectors. They are very precious to us. They define the main goals of the roadmap. They define the industrial needs that we want to address, that they want us to address in the projects. And to cope with those R&D tasks that are necessary to enter those needs, we are also working with our members from the academia and the other research organizations that you can see here as well. Some of them are universities, other are research institutes like the IFREMER, for example, here. We also work closely with the local authorities, mostly regions in France, and competitiveness clusters. In addition to those members, we also work, of course, with non-members. So anyone can join France Énergies Marines projects. So that's why we have a lot of other partners in our projects from the industry or the academia as well. And we are working closely with other research institutes abroad as well. What we do is to build, as was mentioning that just before, a research project starting from the industrial sector needs. And that is a reduction of uncertainties of the business model, reduction of the CapEx, OpEx, of course, impact limitation on ecosystems, and improvement also of the offshore wind perception. And we, through our projects, aim at transferring the results of the research activities to the sector. And we do that by means of numerical models, some new ways, methodologies, and sensors to characterize the environment. We implement that also to standards to reduce the conservativeness of the design processes. We also have projects aiming at subsystem optimization. And to address that, we are organized in 4 departments. And the first one in blue here is the one I am leading, the wind and ocean dynamics. We're working a lot on wind turbulence characterization, measurement, and modeling. We're also working on the wakes of wind turbines and wind farms. We also address the topic of extreme metocean conditions in cyclonic condition, for example, for breaking waves, for example. And we have also a team working on climate change impacts on the offshore wind industry. And finally, we also have hydrosedimentary processes expertise, mostly by means of modeling tools. The second department, the biodiversity and monitoring, are working on marine megafauna, fish and birds interaction with the offshore wind, and they are also working on chemical risk assessments linked to this industry. The system and performance department are working closely with our industrial members by means of developing digital twins and monitoring system to monitor the health of critical components. They are also working on optimization of operation and maintenance, since it is a key driver of the OpEx. And the last topic is also grid interaction and power to X challenges. The ecosystems and society departments are addressing the acceptability of wind energy, and more specifically offshore wind energy, by means of an approach that integrates all the aspects from economics, social and environmental impacts of the wind energy systems. Some technologies that have been developed and that are results from our project in 2024, to give you an idea of what we are producing in our projects. The first picture here is illustrates the digital twin platform that operates on the real wind turbine at sea, and that combines numerical model together with real monitoring data. The second one illustrates material model, mechanical behavior of nylon anchor lines that can be used in design tools by the industrials. The third one is new way of characterizing the turbulence by means of reconstruction of LiDAR signals to characterize the turbulence intensity. And the last one is a platform that has been developed to visualize the bird flow when approaching the wind farms. And all those results, they are, of course, transferred to the industry by means of numerical tools or other methodologies, as I mentioned, but we are also publishing about those results in peer-reviewed journals. We are also co-organizing some scientific and technical events. We also participate to leading scientific conferences. And last but not least, we are part of working groups like the IEA Wind tasks, and we also implement the results where they are addressing, for example, design new design methodologies to be used by the industry in some standards and norms, like the DNV recommended practices, for example. And this is one ambition of the Upscale project, to challenge those standards and come to new methodologies when it comes to wind profile of high altitudes to consider for the design. So I will leave the floor to Jean now, that will dive a little bit more into this topic. Thank you.
Excellent. Thank you very much, Nel. Thank you very much for this presentation of France Énergie Marine. Now, let's start digging into the Upscale project itself by giving you a few words of context. So the wind turbines are exposed to a certain incoming wind profile. This profile is commonly measured by wind LiDAR profilers that are able to make measurements up to about 200 meters, maybe a little bit more, which is consistent with the size of the current offshore wind turbines. But now, as the wind turbines grow larger and larger, not only do they reach altitudes where the standard LiDARs cannot measure anymore, but also where the wind profile is very likely to become more complex. Higher shear, higher veer, higher overall variability in the wind speed through the diameter of the rudder. This greater variability and this overall greater complexity really challenges the simplifications brought by the standard approach that simulates the wind turbine interactions with the atmospheric flow. And this is the very purpose of the Upscale project, characterizing ever higher wind profiles for accurate prediction of turbine performances. now that you have an overview of the context, let's see how we, in the Upscale project, are planning to technically address the highlighted challenges. So the project is divided into 3 technical work packages. The first one is about observations. We will use a new generation of LiDAR profilers that is able to reach unprecedented altitudes that are relevant even for the largest wind turbines. Afterwards, in work package 2, Marion will show you how these observations will be used to reproduce realistic wind fields and wind boxes up to higher altitudes. And finally, she will present how the realistic wind forcing coming from work package 2 will be used in work package 3 to assess the wind turbine performances considering a realistic atmospheric flow. The whole project is managed by France Énergie Marine and is expected to last 2 years between early 2026 and early 2028. Okay, starting with work package 1, which is dedicated to observations. Let's go a little bit deeper into more details. You remember that slide showing that not only the standard LiDAR profilers can't reach higher altitudes, but also the complexity of the wind profile that is increasing with altitude because we are gradually reaching the upper limit of the atmospheric boundary layer. Well, Vesala, who is a partner of the project and also a world leader in LiDAR manufacturing, has recently developed a new generation of wind LiDAR profilers that is able to reach 400 meters, possibly up to 500 meters, which is really highly relevant even for the largest wind turbines, as you can see in the slide. So Vesala offered to provide Upscale with 2 of these new generation LiDARs called WindCube 2.1 XP, and we thank them very much for that. These LiDARs are planned to be deployed for 1 year in the northwest of France, that you can recognize on the map on your right. So you can recognize Brittany and Normandy. So one of these LiDAR will be deployed in the lighthouse of Île-de-Bas, a little bit to the west. This position has been confirmed, and the other LiDAR is planned to be deployed in the lighthouse of Roche d'Ouvre. That second deployment is still under discussion with maritime authorities. If we focus a little bit more on the measurement areas, well, you can realize that they have been chosen because they are located close to future offshore wind farm deployment areas, namely Roche d'Ouvre to the east. Well, although it does not clearly appear on this map, but it's a little bit to the east here of the map, and also the BNO, Bretagne Nord-Ouest area, where a capacity of 1 to 2 gigawatts of offshore wind is planned to be deployed, and which is about 16 kilometers offshore of Île-de-Bas, where our first LiDAR will be deployed. In addition, to secure the relevance of these measurements, France Énergie Marine has shown during a preliminary study that there is a 0.95 correlation coefficient between the wind at Île-de-Bas and the wind at Bretagne Nord-Ouest, at BNO. So we are pretty confident that our measurements will be representative of the wind climate of the BNO area. For your information, this kind of LiDAR deployment for 1 year, 2 LiDARs, is worth about 200,000 euros, including all the mission fees, rental costs, and so on. Finally, we'd like to let you know that France Énergie Marine is currently developing algorithms to infer local wind speed, shear, and veer from distant measurements. This is the NEMO project. They are based on these algorithms. Sorry, they are based on LiDAR measurements, numerical weather prediction models, as well as deep learning methods. And okay, their development is really part of the ongoing NEMO project. So upscale is planned to benefit from the algorithms developed during NEMO to infer the wind profiles in BNO from the LiDAR measurements in Île-de-Bas, including the higher altitudes to make them really relevant for the largest wind turbines. So eventually, what will you get from that first technical work package? First, you would get long-term wind speed measurements that are representative of the wind climate of future offshore wind deployment areas. These, I would like to stress that these measurements are really unprecedented, not only because of their position, but also because they reach altitudes that are relevant even for the largest wind turbines, and also they last 1 year. Then you would also get a procedure to be able to infer the characteristics of local wind speed from distant measurements. So you would be able to replicate basically this procedure to other places of your own interest. Moving on from work package 1 to work package 2 about wind simulation, I will now leave the floor to my good colleague Marion.
Yes, can you hear me?
Yeah, we can hear you.
Yeah, all right. Well, good afternoon, everyone. My name is Marion Coquelet. I'm a research engineer at FEM with a background in the numerical simulation of wind turbines and their wakes. So I'm really happy to be presenting work packages 2 and 3 as a follow-up to the measurement campaign that Jean presented in work package 1. So as Jean introduced, we're observing wind. At the end of the day, we want to use that to characterize the performances of wind turbines, extra large ones in those complex inflows. And there's actually a missing step between the two. And that's really why work package 2 is there. It's there to bring the gap, to bridge the gap between the observations and enabling the simulation of the turbines. So if we break it down, what we get from the LiDAR measurements is time averaged one-dimensional profiles that represent what we measured on a column of air. And what we want to do is elastic simulations of the turbines. But the turbines, they're not evolving in like a 1D configuration. They're like rotating over the whole rotor area, which is 2-dimensional. So we need a 2-dimensional wind field, and we also need it to be evolving in time, so to contain turbulent fluctuations. So what's missing in between is what we refer to as the turbulent wind boxes. So it's a collection of slices of wind fields that we can input onto the elastic simulations. Now we have 2 options that we're considering here to generate those turbulent wind boxes. The first one is the standard engineering approach, which consists in generating a box of synthetic turbulence. So you get a box of small fluctuations, and you superimpose those fluctuations on top of this wind profile that you have, time average wind profile that you got from the LiDARs. This is quick and simple. So this is really the positive side of this engineering approach. The drawback, though, is that it's not really physically accurate. Unfortunately, we cannot just linearly superimpose fluctuations and it works. That's not physically correct. So the other approach that we're really willing to address in this project is to rather use a higher fidelity approach. So the idea is there to say, okay, we measured column of air in the whole atmospheric boundary layer, can we somehow simulate a full atmospheric boundary layer that would be representative of that? And to do that, we're going to use large eddy simulations. The drawback being, of course, that this is quite computationally expensive and also not that trivial to implement. But what is important there is that we really increase the level of accuracy of the flow field that we will generate. And you understood from the first work package that we really want to push on that side to go measure high, get complex characteristics of the wind fields. So we want to keep the level of information quite high also for the turbulent boxes generation. Now we should move on to the next one. If it's moving, no. Okay.
Maybe I can change it for you.
Yeah, maybe it doesn't seem to be reacting to.
Okay, let's go.
Yeah.
Let's see. All right.
All right, perfect. Thanks, Jean. So the LES are going to be performed with the YALES2 tool. So YALES2 is a multi-physics LES platform. So you can go from simulating sprays to combustion to wind turbines. It's really multi-physics, as I said. Of course, we're going to be focused on really two solvers in the YALES2 platform, the one enabling us to simulate atmospheric flows, and the other one about wind turbine aeroelastic simulations. I'll get back to that one in work package 3. The tool is also high fidelity and high performance, and it's developed by the Coria Lab in Rouen, France. We're really happy to have the Coria as partner of this project so that we can make the most of this LES tool. So to clarify a bit what we are aiming to develop for the project, the idea is to really automate this procedure to go from LiDAR measurements to LES of the atmospheric boundary layer. I will say ABL in the coming, or it's going to be pretty long. So why is it challenging? Because the parameters that you need to provide to the LES to run and to obtain this ABL, they are not the wind profiles that you measure with the LiDARs. They are typically the geostrophic wind, the heat flux that you're going to have at the wall, the temperature that you're going to see at the wall. When I say wall, I mean the sea surface. So you're going to define those parameters, run your LES, get a box of wind, and then out of this box of wind, you can compute the statistics and see what resulting profile you've obtained. And the whole challenge is this going to be representative enough or of what we measured with the LiDARs, yes or no? And if the answer is no, then we need to update the ABL parameters and try again. Now, of course, this is LES. This is quite expensive. We don't want to do trial and error. So we want to have a procedure that automatically does that and that controls the ABL parameters. So that's going to be really the technical challenge, the scientific challenge that we're going to be teaming up with Coria to address in work package 2. And once we have found the method to do so, and we managed to reproduce the profile that we measured in work package 1, then we're really happy because this big box here is representative of the ABL conditions that we saw, that we measured at BNO, close to BNO, and we can extract from that slices of wind that we can then input on our aeroelastic simulations. All right, so what you get out of this work package, I would say 3 things. The first one, we mentioned measuring high up in the air. With the LES, you even get more than that. You get to reproduce the whole ABL that would be representative of those measurements that we had from the LiDARs. So we gain more physics, more insights into the physics of the atmospheric boundary layer at high heights. The second point is that if you're interested in larger simulations, you'll also be happy to benefit from this automated procedure to go from the LiDAR measurements to the LES of ABL. And the final point is, if you want to try on your aeroelastic solver the wind conditions that are representative of what happened at close to BNO, then you get a realistic wind box that you can use right away with any aeroelastic simulation tool. Now, of course, this part here is where all the fun is. So we also want to do the exercise. And that's why we have work package 3 here. We're basically going to use all the information that we've built up to perform the simulation of those extra large turbines we mentioned in the introduction to assess their performances in realistic atmospheric flows. And the first thing to kind of contextualize this work package, it's always the same story when you talk about simulation. There's always a trade-off between computational cost and the fidelity of the method. I also highlighted it earlier with the way to generate the wind boxes. And when it comes to aeroelastic simulations, I would say that there are mainly two categories. Either you have a solver that is standalone, so that really focuses on the forces exerted on the blades given a specific inflow, but not much more about how the flow evolves downstream of the rotor and so. The other method is to use CFD coupled strategies where we have an actuator line or actuator disc that represents how the blades react to the flow, but we also have the full CFD running together to provide the evolution of the flow field. Now, again, you understood that we really want to go for this high fidelity. So of course, we want to try this CFD coupled approach. And this is what we refer to in those slides as, if it's willing to go. Maybe Jean, I need your help again.
I'll try. Let's see.
Yes, perfect. So we want to go for a high fidelity simulation tool chain where we go from the inflow, which is the inflow we just discussed before, right? The LES generated wind boxes. We use an aeroelastic solver, which is LES coupled. And in this case, we're really happy again to make the most out of the YILS2 platform. And out of that, we managed to retrieve the whole performances of the turbine, so power, loads, but also wakes. And with that, we have this whole high fidelity simulation tool chain that can provide us with really reference results of how a large turbine would behave in a complex inflow similar to the one that we measured in work package 1. Now, we understand that not everyone is willing to pay the price of the LES for every case. So we're also willing to assess what the standard engineering approach can do. So in that sense, we're going to be using synthetic turbulence boxes, as I mentioned earlier, use them as an input for a standalone aeroelastic solver. We're still open on the solver, by the way, but probably a BEM-like solver. And out of that, we get typically power and loads. We don't get the wake, unfortunately. And we can compare how these results compare with the high fidelity simulating tool chain. And maybe we can also do actually some crosses between the tool chain. So maybe we can try the LES generated wind box in the standalone solver. Like, is it good enough to represent the complexity of the field to get the right performances? Or maybe is it good enough to just have a good aeroelastic solver, even if the flow field is not the highest quality? So we're really willing to challenge the standards and see what is good enough and at what cost. So what you get of this work package as a summary is, first you get the reference results with a high fidelity simulation tool chain of the performances of extra large turbines under the realistic inflow conditions measured in work package 1. Then you get the comparison of those results with the standard engineering approaches, and you also get a characterization of the limitations of those engineering approaches. And I think with that, I will leave the floor back to Jean.
Thank you very much, Marion. I'm sure that now our audience now can't wait to join the Upscale project. So let me show you how easy it is to join Upscale. So first of all, we are talking about a project of about 1 million euros. And amongst this 1 million euros, there's one part that we call mutualized costs that reach about 550,000 euros, and that is operated by France Énergie Marine. They cover basically the France Énergie Marine's human resource expertise allocated to the project. They cover service costs, investments, possible investments. We also have a postdoc that is budgeted in the upscale project, and of course the measurement campaign that was presented in Work Package 1. To benefit from the outcomes of the project, our partners are requested to financially contribute to this mutualized cost part. In more details, each large groups and medium-sized company is expected to contribute by at least 40,000 euros to the mutualized cost, and 50,000 euros from small SMEs through basically cash contribution. Now, there are two good news. The first one is that for French companies, your financial contribution can benefit from a Crédit Impôt Recherche. The second good news is that as long as the total amount of our private partners' contributions reach more than 150,000 euros, then the French government complements up to 550,000 euros through the France 2030 investments plan, because France Énergie Marine is an institute for energy transition and can benefit from that investment program. Basically, if we want to make it short, the total budget of the project is about 1 million euros. France Énergie Marine operates 550,000 euros, including the France 2030 investments, and the cash contribution expected from our partners, our private partners, is 15,000 euros from small SMEs, PME in French, and 40,000 euros for large groups and MSCs. Part of which can be covered, part of this contribution can be covered by, part of this cash contribution can be covered by Crédit Impôt Recherche. So basically, through your contribution to upscale, not only can you very strongly leverage the amount of your financial contribution, because France Énergie Marine has a special status of Institute for Energy Transition, but also can you benefit from the outcomes of a 1 million euros project. So to finalize this presentation, I'd like to give you a short reminder of what you will get by participating to the upscale project. Work Package 1 related to observations will provide you with a unique database of wind profiles close to future offshore wind deployment areas at altitudes that are relevant even for the largest wind turbines. It would also give you an innovative procedure to infer the local wind profiles from distant measurements. And for this work package, we receive a very significant support from Vesala, and we also benefit from the outputs of previous research programs from France Énergie Marine. Regarding work package 2 about wind simulation, you will get a procedure to generate large eddy simulation flow fields that are consistent with LiDAR measurements, and a database of high fidelity, realistic wind boxes that you can plug basically or use with your own aeroelastic tool. And to address this work package, we will receive strong support from the CORIA. And finally, for work package 3 that CORIA will also be supporting, you will get high fidelity reference results of extra large wind turbine performance, considering a complex inflow, And you will also have much better insight of the limitations of the standard engineering approaches for the characterization of wind turbine performances in realistic complex inflows. Thank you very much for your attention. Please let us know if you already have some questions. We are exactly on time. This is awesome.
So Jean, there is already some question in the chat. In the conversation, first there is a question from Marc Guyot about when we were talking about when Marion was talking about a standard engineering approach and synthetic turbulent box. Do we mean modeling wind using TurbSim, for example? So
Yes, that's what we're referring to. We're open on the software. I think this is not decided yet, but this is typically TurbSim-like tools.
Yeah, thank you, Marion. Another question from Frédéric from Vesala. I understood that one input for the simulation is the shear profile. Does the TI profile is also considered?
For me or for you, Jean?
Regarding the TI profile, well, we are maybe I'm not sure if Maxime is connected to the webinar. Oh, but maybe he doesn't have okay, his microphone. We've been discussing quite a lot about the turbulence profile. Yeah, indeed, there are two different ways of characterizing the turbulence profile, with one single lidar or two lidars. And
Jean, I'm here.
Okay.
Sorry.
Okay. Excellent. Okay, so Maxime will answer this question. Thank you, Maxime.
Yes, so we have developed a way to measure turbulence profile at France Energy Marine, but the requirement is to use two wind cube to form a dual lidar setup. With this, we have only one source of error instead of three when we are using the one lidar, one wind cube in particular, or any other actually. So yes, it could be a good opportunity to use this setup at Ile-de-Bath, but actually it's up to you, Jean, who decides whether we are using two lidars at one site and we will be able to get proper TI, or if we have two lidars, another solution will be to deploy the lidar at two different locations, and if we are deciding to go for this solution, so we won't be able actually to provide proper TI profiles. So
yes, indeed, we are currently considering two different deployment areas for the lidars, because we would like to have two representative lidar measurements for two different offshore wind deployment areas. But as I was mentioning, the deployment at Ile-de-Bath is confirmed. The deployment of the LiDAR at the Roche d'Ouvre is still being discussed. And in the case the second LiDAR cannot be deployed at Roche d'Ouvre, then we would go deploying two LiDARs at Ile-de-Bath in a dual setup. So we would be able to make high performance TI measurements.
Thank you, Jean and Maxime. There is another question in the Q&A from Loïc Scouff. Would the calibration of the LES simulation be based on the original LiDAR measurements at Ile-de-Bath or the adjusted measurement to BNO location, inducing additional uncertainty?
I think that one is also open. So that's to be discussed. Indeed, we agree on the fact that if we go for the BNO location, we add a step, so we add uncertainty. I think the key thing really of work package 2 is to manage to develop a methodology such that at the end of the day, you just want to reach a profile and you can reach it. Now, if we decide to do it with the BATS Island or with the BNO site, we can go for it. That would be my answer.
Okay, thank you, Marion. And the second question of Loïc is probably addressed to Robin. Also, how is the adjustment between the LiDAR measurement and the offshore wind farm location handled at high altitudes where no measurements are currently available?
Thank you, Neil. So I'm not exactly sure I understand the question. We are working on this extrapolation question within the NEMO project already. And the idea is to use numerical weather prediction to correct them with existing LiDAR measurements and then to extrapolate with uncertainty estimation to other locations. And the idea is to use deep learning models to ingest maximum amount of explanatory variable, environmental variable, to explain the differences between the coastal and offshore locations. So this is really ongoing work. So I cannot be more specific than that for now.
Okay, thank you, Robin. I cannot see any more questions in the chat. Maybe I can add that if your entity is interested in joining the project, then we expect an email from you by the end of this month, and the firm confirmation within 2 months from now. That will be kind of the schedule that we need to follow. So don't hesitate to send an email to Jean, and I guess you have the email on the screen right now. Yes. Any questions? If not, then...
All right. Well, if we don't have any more questions, I just need to thank you again very much for attending the meeting. And just like Neil said, really don't hesitate to contact me directly if you need any additional information. And again, if you want to join the project, please raise your hand quite quickly. Just like Neil said, within a month, basically during October, the latest. Thank you very much.
Thank you, everyone.
Thank you. Bye-bye.